Okay, welcome everybody to tonight's lecture, and welcome to everybody who's viewing this across Zoom as well. Tonight we'll welcome Matt Gavin, who is going to give us a design manager's view of small modular reactors, which I guess is quite opportune and apt on the back of COP26 that finished last week. I know everybody's fed up of hearing about COP26, but this will be really interesting as opposed to some of the other stuff, I'm sure. Gavin sort of started his career through a modern apprenticeship at Pandrol. Did a bit of time with Siemens after that, Chesterfield Special Cylinders. Then you moved to Rolls Royce from there, yeah. And along the way, you've got a bachelor's and master's degree from Sheffield, and you're also a chartered engineer. So welcome to, and thank you for coming. And we're really looking forward to seeing the presentation. So thank you. Over to you.
Yeah, thanks very much for that introduction. Nice to see the online stalking is working out all right. So no secrets anymore. Yeah, thanks everybody. Thanks for the opportunity to come and talk to you today about what is a very exciting project and started to really hot up. SMRs is something that's kind of been bubbling away in the background, but doing bits and bobs, ticking it along, getting a little bit of investment, losing that investment, rapidly going on now. But now we're seeing a real kind of, I guess, excitement around it, not just from us at Rolls Royce SMR, but also a lot of government backing and a lot of private investment backing as well. So we're in a really exciting place. Hopefully I can share some of that excitement with you today. Just like to introduce my colleague over there, Jason Swan. He's our sort of materials specialist, I'll call him. Might not like me saying that. So if you've got any hard questions, you can ask him, and I'll take all the glory at the front here. So that's fine. Oh, I forgot my pointer. Thank you. So a bit about me, I guess. Just had a little bit of a check in history. I've got a young photo and an old photo. I don't know if that's the 12 years in the nuclear industry that's done that, or the 2 children, but something's made that happen. Yeah, I've been an engineer. Like I say, started as an apprentice. Did my apprenticeship with a guy that's in the room just over there, actually, just coincidentally. And I'm now an engineering manager, so my role's changed. I've still got a lot of interest in the technical side, but obviously I've got a lot of people now and a lot of things to do with processes and a lot more sort of driving the programs, budgets, that kind of side of it. I've got to believe, I came from a submarines background, so sort of military application of nuclear. I moved into a civil, I really do feel passionately that nuclear's got a big part to play, certainly in our future. It's part of the energy mix, it's not the only answer. There's a lot of answers, there's a big mix of sort of energy that we need to sort of generate to get to net zero and achieve some of the targets that we can promise through COP26. We often joke that we're saving the world. We're not saving the world will be finding out us. We're saving mankind. Is kind of what we joke about. So that's kind of we try to. That's our mission. We're part of that. We're trying to be part of that. We're trying to make this a grand sort of endeavour and hopefully inspire a few people along the way. Because this is truly a UK capability building project, a capability building programme. It's going to bring a lot of investment to the UK. It's going to give a lot of jobs to the UK. It's going to sustain the supply chain around the UK as well, which is something we're very excited about being part of. So if these images are a bit iffy, I apologise because I had to downscale them so that I could send the email through to you guys. So apologies to a bit grainy, but really the sort of SMR was born out of a recognition that the energy mix it's changing. It's there's going to be a massive need for clean, renewable electricity and a balance of technologies to fulfil that demand. I mean, some of these numbers when I first saw them, I was staggered. Things like sort of data centers to support, cloud networks and that kind of thing. The amount of power that they demand is just staggering. Bitcoin, 30 gigawatts per annum. These are staggering numbers, and they're only due to go up. A lot of our sustainable energy sort of ambitions are really directed around clean electricity, electric vehicles, and a lot of that sort of side of things that are going to ramp up in that. The UK infrastructure is all around generating clean electricity. So we see nuclear as playing a key role, not just SMRs, but also large scale nuclear as well. So really SMRs can support a lot of other sort of needs as well, such as hydrogen production, which is probably part of the future. You know, there's debates around the effectiveness of hydrogen for this kind of thing. Sort of sustainable aviation fuels, which is a hot topic. Obviously, Rolls Royce has got a big interest in that area. Part of the COP conversations last week. But you know, desalinization, and this is really a product that isn't just for the UK. This is a product that this could be an export. This could be a future UK export to give, you know, the UK a position back at that table in terms of the real technology provider in the world. So into a lot of real applications globally, but that perhaps we don't necessarily need in the UK. So really, we're in a position where driving the SMR, it's the project's key around a number of key requirements. Really, this is not about major technology innovations necessarily, unless they're in the right areas. This is not around, I guess, changing the landscape of nuclear in terms of its technological application. This is all around, can we make nuclear deliverable? Can we make it cost effective? Can we make it investable? And they're the three real key drivers for the SMR program. You know, this is not innovate for innovation's sake. This is not tinker. This is basically get something right, make it low risk, get it through. And our innovation will really come around with how do we deliver this power station repeatably and sustainably, and you know, in a way that's value for money, but also and can attract investment. So that's really where a lot of the key drivers come. It's not necessarily just around the reactor technology or the nuclear technology. I've got a video to play to just set the scene. Quite sure how to play that with it.
The UK target for net zero carbon emissions by 2050 is ambitious. To achieve this, we need more clean electricity to power a future that enables us to develop, to grow, to prosper. Our target to decarbonise cannot be met by intermittent renewables alone. The challenge is on us all. We must act now. At Rolls Royce, we have the answer. The Rolls Royce SMR is a low-cost, clean energy solution. Made in the UK for industrial, utility and energy customers. A factory-built nuclear power plant, transported to site as modules and assembled in a specially designed on-site factory, radically reducing construction activity, creating a fully integrated nuclear power plant, and an architecturally beautiful structure. The Rolls Royce SMR is scalable, versatile and innovative. It can be deployed across a variety of applications, creating new opportunities to meet a range of clean energy needs. Capable of operating at availability levels of 95%, 24 hours a day, 7 days a week, for 60 years. A twin SMR can also provide 100% availability of clean electricity for customers who need an always-on solution. This unique N+1 configuration not only ensures access to clean energy all day, every day, but will also produce large volumes of surplus clean power, which can be used for other off-grid solutions, such as hydrogen production, synthetic aviation fuels, and desalination. The Rolls Royce SMR uses proven and commercially available products, allowing it to deliver a competitive, low-cost solution, creating delivery certainty, reducing risk, and building investor confidence, and creating jobs. Lots of jobs. The challenge is on us all. We must act now for all our futures. We are Rolls Royce. Our SMR is powering a clean energy future. We are pioneering the power that matters.
You're going to all hear that. But yeah, our marketing guys have obviously done a real job on that. It touches on some interesting points, and I think I'll draw a little bit more out of the presentation here. But as you can see, like this power station is designed really to sort of kill a lot of the nuclear stigma. You know, public perception is really key in this project, and we're looking at, you know, it's a very aesthetically pleasing design. You know, and it's really around how do we integrate this into our society, because this is going to be a bigger part of the UK society and the world. So, you know, this is part of the challenges that we're facing. Rolls Royce. So why Rolls Royce? Rolls Royce have got pedigree in nuclear, obviously through the submarines program, but also in civil nuclear, supporting a lot of large build projects in Point C, especially like most recently. A lot of experience through the submarines of designing nuclear plant, maintaining nuclear plant, and supplying nuclear plant. We've just been through a new redesign project for the submarine business, which is, you know, a first of a kind in the UK in terms of the new design. It's once in a generation type stuff. So we have built a decent capability there. That's not to say that capability can now just be lifted and shifted. There's a whole load of skills needed in the country, in the UK, to sort of support the SMR endeavour and the new nuclear endeavour. But we, you know, I guess the roots of all this, and the reason that Rolls Royce and Rolls Royce SMR has become a sort of credible option because of that pedigree that we're building into this. Lots of design philosophy type things as part of the programme. Like I said before, this is not about changing nuclear as a technology. It's about really using the current technology that we've got and delivering it in a more reliable way. So small is, you know, a relative word. This is a deliberately powered power station. It's deliberately powered in a way which gives it its size, essentially, where we try to reduce a lot of the build challenging areas in terms of footprint, because footprint costs money. And a lot of the kind of expensive real estate, we're really focused in on making that as compact as possible. Hence the word small in the acronym there. We're looking at about a sort of power station, a couple of football pitches, really, in terms of it's the armadillo, as we call it, which is like the sort of hazard shield that surrounds the power station island. Modular is a key word that we use a lot. Modular is, this is about taking a lot of that activity on site was problematic, was risky, was costly, and bringing that off the production critical path into factories. That's why Rolls Royce has got some pedigree here that we can build upon, you know, in terms of modular build, in terms of factory sort of manufacture, factory assembly expertise that we can bring to this design. That's not to say that that's a simple shift from sort of the aerospace side of the business. It's not. It's an absolutely new challenge that we're, you know, getting to grips with, and that's really a big part of this. The key thing is this is a turnkey. This is not a case of delivering these parts up to a customer with lots of contractual complexity. This is a turnkey. It's a product. Trying to turn this into a commodity rather than into a major project. So that's kind of the part of the philosophy stuff that we're trying to get after. Similar slide, I guess. We've done some studies. There's been a lot of sort of background studies, and there's a lot of studies out there in the industry as to how the energy mix will look, and how we fulfill that energy mix. There's a lot of obviously love for renewables, and so they should be. They are part of the solution as well, such as wind and solar. But there is a demand for base load, you know, reliable 24/7 base load that nuclear, the only really nuclear can provide to be clean. The storage, you know, power storage technology is not quite, you know, in a place to be cost effective, but that will come online in the next sort of 10, 20, 30 years. That's to be seen. But there is, you know, there's a global demand as well as a UK demand for clean, low cost sort of base demand energy. So that's what the SMR will provide for. Will provide once it's in place. Lots of studies. We're really early in the concept phase at the moment, but there's a lot of studies that being conducted on sort of localized levelized cost of electricity compared with other technologies. You know, this is a business case at the end of the day. This is not overbuilding nuclear and that's it. This has got to be value for money. It's got to return on that investment. Got to make this investable. You can see obviously some of the studies around the cost of electricity, solar, wind power. You know, obviously great, quite low cost energy sources. But once you consider storage, once you consider intermittence in this country or in areas where they're not really viable as technologies, you know, SMR is really starting to look like a competitive sort of endeavour for us to, in the UK, to really invest in. And it's that kind of business case that's really got the interest from the government, got the interest from the investors to push forward. And it's what got the interest of the Rolls Royce board as well. So, you know, in terms of this getting off the ground in the early days, that was all very more key in really developing that business case. Some facts, if you will. So 470 megawatt electrical output from about 1200 megawatt thermal. So that's what we're looking at the sort of reactor plant. 50 hertz, obviously in different markets that might be a bit of an issue with 60 hertz markets. That's something under consideration if this is going to be a product with the market multiple times, which is what the idea is. Choosing proven technology, so proven pedigree technology. Yeah, this is not a Gen 4 reactor. This is not an integral reactor. This is a PWR, as you probably know it. If you're aware of that kind of technology, this is not a changing the world, like we said, in terms of nuclear technology. It's about innovative ideas and innovation in delivery and in cost certainty. It's delivered as a turnkey. I've touched that, looking at 4-year construction. I'll go into a little bit why we think that's a viable target. That's racy. All underpinned by safety and security. Obviously, the design of the burn, the hazard shield, that's all deliberate. That's not just to look nice. There's functionality within the entire site design there to enhance security and enhance safety from external hazards, such as, you know, people wanting to fly airplanes into it or people drive trucks into it and things like that. So there's a lot of functionality built into that very pretty looking power station, and that's deliberate. You know, the architects have had a really good go at that, maintaining that aesthetic look while still maintaining that functionality is key. And we've all played a part in that, with it being bringing the size of the reactor down, bringing the size of the sort of footprint of the site down. Cost, lots of cost targets, lots of things to look at. The scary one, you know, on grid early 2030s, that's only the targets are coming left of that. So 2030s is I guess a decade that we've picked, but that's early 2030. That is like just the turn of the new decade. And earlier if we can, there's a lot of demand on getting this technology, getting this power station up and running, you know, in the next 10 years. That's what we're looking at, which is a challenge, you know, under any circumstances. It's obviously underpinning reactor requirements. This is still a nuclear plant. What the key is, what the key thing in this is, we've got to still meet things like, you know, regulators. We've got to meet safety targets. We've got to meet objectives of safety. We've got to deliver a safe nuclear plant. It's not to go without saying. And there's some underlying sort of principles that make that a reality. But there are things we can trade, and the trades are really important. Like I say, the size of this power station is deliberately designed. It's not just, oh, we'll make it small so it looks a bit nicer. There's some real deliberate trading in there to make sure that we can, you know, maximise power, to really bring down that cost of electricity as far as we can. Reduce capital cost, make it deliverable, minimise build time. All of this stuff is really, these are the problems that plague large nuclear. These are the problems the SMR has been designed to solve. So there's been a lot of thinking and a lot of bullish trading around how important are all these requirements and how do we trade them off against each other to get them up to the most optimum SMR design. Kind of touched these principles before. I mean, these, because the key, this is the kind of, I guess, the underlying message about SMR is we've got to be cost effective, we've got to be able to deliver this, and it's got to be investable. Some key enablers in there, so proven technology, risk for regulatory approval, all of that kind of thing has got to be minimised, minimise that risk so that we can deliver this on time. Simplifying standardised equipment, so something on we're looking at the whole power station, the power that we've got in there is standardised across that whole power station. We're not plagued by contractual boundaries, we're not plagued by sort of interface challenges. We're in control of all of those. So we can look at commoditising a lot of our components that might be one-offs in a standard nuclear build. So we've got a lot more opportunity there for standardisation. Minimising the site work. Like I say, I've got a slide of how we're going to enable that. But minimising site work is key. Like concrete pour, really expensive, you know, time consuming, dirty. So modular concrete is something we're looking at. Modularisation of systems, subsystems, and components is key. Commissioning off site. They're all real key enablers to just minimise that work we have to do and actually getting on the nuclear site. Deliverability, so factory built commodity is a key one. We are looking at investing in facilities in the UK. So we will have a heavy pressure vessel factory, large infrastructure project. We will be having a modular build factory, and we will be having another factory I can't remember the name of, as well as the side factory. I think I've got a slide on it, so we should get there. So this is a case of really drilling into that factory build mentality, that production line mentality into nuclear, which is obviously where the novelty lies. I said a few times, this is deliberately designed. This power station is deliberately got the power output that it's got. Really, so road transportation is a key requirement for all of our major components. So essentially, the power output is governed by the fuel, the core design, which sets the size of our sort of major vessels, the reactor pressure vessel. That's got to be road transportable, so that's designed within an envelope. This is so that we can transport it not only to the sites in the UK, but also in Europe. So we've got a load of transportation limits set on our design, constraints around our design to make sure that we can actually move this. We can build off site and we can move to site. We haven't got to do any factory, any site work of, you know, high sort of critically sensitive welds or anything like that. We can do all of that on site control conditions. And modularisation, so we're looking at pretty much standard footprints for modules. They're based on ISO containers. So there's nothing clever here. Just it's all about how do we most efficiently ship sub-assemblies and subsystems or systems. So we've got a footprint essentially that we've got some interlocking sort of measures and ways to assemble this on site when these modules arrive as fully commissioned units, which is again part of the innovation. And also, like I say, using commercial commodities off the shelf sort of stuff. We are looking at really pushing that as a, you know, how safe, how reliable are these components need to be, and we drive to a more commercial off the shelf product and build inherent safety systems elsewhere to make that more deliverable. And the other factory is the civil modules, which I didn't forget, so apologies. Yeah, 3 factories, so major, you know, talks about lots of jobs, lots of UK opportunity. You know, there's some major sort of infrastructure going to be going up around the country. Locations to be decided. You know, there's a lot up for grabs. There's a lot of political sort of, I guess, discussion around that as well as to which areas in the UK need the infrastructure, need the job, need the investment, and how best do we sustain that. You know, obviously Sheffield, a big industry partner in the UK, and you know, there's big companies in Sheffield such as Masters that are very much in the mix for that kind of work. The MRC doing a lot of work for us in our manufacturing development work and some of our feasibility studies for this manufacturing technology. So yeah, there's a lot of jobs kind of coming this way already, as well as around the country. We're obviously going to be a nationwide project. We can't source all the staff we're going to need for this in Derby or in any one location. You know, with COVID, we've all worked from home. So we're trying to enable that much more some kind of global mentality when it comes to this, rather than it being a kind of hub within a certain number of areas in the UK. It's going to give opportunities for everybody. So lots of exciting stuff to come. The designs of these factories are fairly, on paper, obviously fairly advanced. Site ship, but we are, you know, 18 months, 2 years away from digging foundations and get these factories over. This is not a long-term endeavour. This is a very short-term sort of aspiration. The 4th factory is site factory. So site factory is an idea born out of basically analysis of what plagues nuclear new build, large nuclear new build. Weather plays a massive part, believe it or not, in downtime through a year. Weather is a big issue. So the site factory is designed to create a canopy over which we can work sort of all year round. to really make sure that we can get this on, get these power stations built efficiently, effectively, and over a short period of time, so that we avoid like lengthy delays and lengthy costs when it comes to delays. The delays on a nuclear new build really what affect the long-term financing of these projects, which make them unaffordable. So that's really a real drive that we're going after. And this site battery infrastructure, you can see the concept of down there, is designed to really enable us to be 24/7 build program essentially all year round. Yeah, so there's some sort of key bits that I just wanted to draw out on the basic design of the power station. So I've talked about commoditizing quite a bit. That's a key enabler. To do that, to put this all over the world, we've got to really understand the seismic issues around where these might go. There's interest from various countries that have all very different challenges when it comes to the terrain, to the type of rock, to the seismic sort of isolation. And I'm sure everybody is aware of what happened for Fukushima and why that's such an important issue. So this is going to be a power station that's partially, I'll say, but mounted on a seismic bearing, so that we can isolate any sort of secondary ground response, any sort of seismic spectra issues from around the world, so that we can have a sort of one-stop design of the SMR that we could deploy many times. The redesign costs on moving like a design from the UK to a different part of the world is, part of the even from established designers is where a lot of the spend goes. So we're looking at really turning this into a deliverable product around the world, so it can be built many times. We've got all the effects of the learner, the manufacturing processes. We can learn, we can get faster, we can get cheaper, and we can really deploy that. So there's a lot of sort of thought gone into how we turn this into a product rather than being a sort of one-off special build power station, which is really the enabler for the drivers that we're trying to achieve. There's a little model there of Reactor Island, which is where I'm working in there. So I'm trying to deliver the components into that mesh that is there, as you can see. So a very compact PWR, a very compact sort of power plant, really. Three loops. So we've got three sort of conventional steam generators. We're not doing anything clever with the blackout with the steam generators. We are buying things that we know and buying things that we understand. We're using standard fuel assembly essentially, and a lot of the components in there we're familiar with fuel to any plant around the world, albeit we have different challenges in terms of space constraints. So we're looking at minimising the height of containment. Containment is a big expensive animal. So we're looking at how short can we make these steam generators, how short can we make containment to really enable still to get a maximum power out of this plant. So a lot of trade-off happening in there to make sure that is buildable, integrated, that we can modularize it, deliver it, and back below it, basically. I guess the key innovation, and really this is again to enable this to be deployed anywhere in the world, is we're a boron-free design. So for those of you that understand the nuclear industry, that obviously boron is key for controlling reactivity. We're taking that away, which is a little bit of a concern. So we have to use our control rods essentially to control our reactivity only. There is an emergency injection system for boron to if it goes super bad, but that's essentially where a lot of the challenge around the component innovation comes from. Just through that decision there to go boron-free, which enables us to have a lower impact on the environment and really deploy this in more places around the world. Probably touched on these kind of things before. The groundworks and the seismic bearing we've covered. This is the aspiration is 90% of this is factory built, not site built. That's obviously a target that we're going after, and that's not just of the traditional sort of steel components and the frames and that kind of thing. We are looking at concrete modularization as well. So this is not considered a kind of mega project. It's just a delivery assemble project, and you're up and running, and you've done a lot of commissioning that site. So there's a lot of innovation and thinking in that area. So this is kind of showing how we're kind of our journey from this mega large nuclear project down to where the SMR needs to be. So a lot of it is enabled through plant design, making sure that we've got a repeatable product and that we can fabricate this off-site, we can deliver it, looking at the logistics and the low capacity of facilities and that kind of thing. A lot of it is done there. Site activity, so we've reduced the footprint. We've got a site factory which I've covered, and we're looking to decouple the civil works from factory scope. Interfaces, so trying to make this much more simple in terms of physical interfaces, but also sort of contracting structure. Commercial simplification, so we're a single SPV now, after the announcement of earlier last week. Rolls Royce SMR is its own entity that can receive investment, receive funding, and deliver a power station. That's where we are now. So we're looking at obviously enabling our supply chain to really help sort of turn this into a turnkey solution. And it can help deliver all those things. So there are lots of potential benefits, not just conventional sort of electricity generation. There's a lot of spin-offs, which makes this quite an attractive proposition for a number of reasons. And that just goes into the business case for the investors. It's just an overview really of where we are. So we've just come out with what you can see is phase 1 there, 2021. Essentially, that's these phases are really driven by cash. I'll say, it's as crude as that. From 2016 to 2019, the project had a lot of ups and downs, a lot of little bits of investment from Rolls Royce and some supporting partners, but very much let's see if this has got kind of legs as a project. So in that phase, obviously ramping up towards the back end of 2019 when phase 1 hit. And phase 1 was a joint funded phase. We had 36 million in total, which is not a lot, very far. That was half funded by a consortium, of which Rolls Royce was a part of it, but a lot of the other partners that bring in a lot of expertise to this to build like the groundworks, to build all the other elements that make up the SMR. Rolls Royce has brought the plant design expertise, and half funded by the government. So that was, the most funding we've had today was in that phase 1, which enabled us to mature quite quickly. We ramped up the team, and now people I'd say in the team, which again isn't a lot, but an endeavour of this size. But phase 2 is game changing, and that's why you'll hear a lot about us on the news over the last 2 weeks. Phase 2 is a game changer. This is a 500 million essentially, £500 million, half of which is public money, half of which is investment money that's coming into that phase of it to really get this design through to the step 2 of the GDA, the Generic Design Assessment of the ONR. So we're really ramping now. This is an exciting point. We've had a lot of sort of false starts, if you will, through the project, but now there's a real significant intent really around this technology, around the UK government's commitment to it. And obviously COP26 has really helped us secure a lot of support for this kind of endeavour. So yeah, not to be sort of sniffed at really. We're probably going to put our resource up by 500–600%. I can't remember the overall numbers, but we're in over 1,000 people into the project, which is an exciting thing. That only runs from 2021 to 2024. Then a lot of our work in phase 2 is not just around developing the design, developing the factory solution, developing the manufacturing. It's about developing customers. So customers in the UK, customers abroad. So there's a lot of work going on business development, on engaging a lot of countries that want this technology, that want to become part of this journey that we're on. So a very exciting time. And then from that point on, once orders are received, then that's it. It's go time. So a lot of work to do in the next 3 years. Goes without saying, very busy time, a lot of challenge, finding the skills to fill these roles in the UK at the moment is going to be tough. We need help doing that. We need to make sure that we bring in the right people, make sure that we get the right training in place, and we really upskill the UK into nuclear. And that's not just within Rolls Royce SMRs, within all the supply chain partners and all the suppliers out there that will be a part of this journey. And that's about all I had. So if there's any questions, guys, we'll be happy to take them. Or Jason will.
Is there any questions? Anybody? Yes, well,
Well, I've totally misunderstood this project, and I can understand you're doing a brilliant new idea in a way, but I thought the whole idea was to take the primary circuit from the submarine and get one of those out and working quickly with its chosen term, like whatever. I would have thought there's quite a lot, you're going to have to spend a lot of time on this project, whereas people really need it now. Wasn't that the benefit of taking a submarine reactor and just civilizing it?
Yes, and I think there's a sales pitch in that from a Rolls Royce point of view. Notwithstanding the security implications of that alone, just to lift and ship that, that's not an issue. The civil demands are very different in terms of the civil power generation. It's very much, a submarine has to do lots of different speeds and have lots of different power generation and all that sort of stuff, and lots of different demands on it. And in a way, we've shifted the expertise, we've shifted a lot of the knowledge from the submarines program, but just shifted the product into that, necessarily the right option for the result, for the trading of requirements that we're doing in terms of buildability, in terms of modularization. Having said that, we've as a business learned a lot from the Dreadnought program. That was a serious undertaking in itself. A lot of that knowledge and those skills and that capability is can come across, but there are limits to that due to the nature of that business, as you can appreciate.
Really, I would have thought was that investors would run a mile if there's too many unknowns, and I would have thought you're in a situation where really the government has to stand up and order the first one, buy it, put the money up, and get you going as fast as possible. Otherwise, some people will pinch this, I think.
Yeah, and there's competitors, and certainly in a lot of the US and a lot of places where they've got you are competitors. There's room, there's room for the UK SMR in the market. That's what we've found. There's room for it, irrespective of the competitors, irrespective of the sort of development of renewables. There's room for UK capability. That's an interesting point about whether the government can order an SMR. Are they going to be the first customer? That's certainly where a lot of the thinking is. Who knows? We've not said that yet. They've given a real serious signal of intent with 250 million public money into this project, and that's been backed by investments. But you're absolutely right. Investors run a mile of closure unknowns, which is why the sort of really technically risky areas of the plant we have opted for chosen for proven technology. We're not innovating in that area. We're innovating in the delivery of that technology rather than in the actual that technology itself. We're not building. We are where we've got high risk areas. We've done studies into could we bring that capability into the UK or should we use capability from elsewhere? We are using capability from elsewhere where that could never, either times us out of 2030 or prices us out in terms of competitiveness. So there is an element of addressing that risk through expertise that already does exist out there. Steam generators as an example. We don't intend to build a UK steam generator capability. That's a huge endeavour. That's a 15-20-year program itself. So we are using a supplier that supplies its tubes to other power stations already within this kind of size band.
So taking the submarine steam generator wasn't an option.
okay, gentleman there.
Two questions, please. First, can you tell us something about the waste management issues? Particularly, you can't moisturise the disposal and storage of waste. And is the waste profile for a given output of electricity equal to more or less than conventional PWR design system? The second question concerns containment. In a submarine, your secondary containment is sea water. There's no detail in your images of nation primary and secondary containment of the reactor. Is this an issue that's going to require particular attention? given that you're talking about small dispersed land-based operations?
It's a great question. You're delving into an area that's not my expertise in terms of waste management. I guess in terms of the waste production from this, this is, this is proven. We've chosen a waste, a fuel design route and a waste management route that's proven. We're not straying outside of current practice, known technology, known sort of procedures in that respect. And obviously, scaled, but this will produce similar waste to standard PWR, large plants. There's, that is an issue that will be constantly questioned, I think, in the development of more nuclear. Obviously, waste is quite a small byproduct of a nuclear plant compared to, say, a plant or another type of plant in terms of its pollution and its issue. But absolutely, that's a fair question. That's something that we need to keep our eye on as a project. Like I say, it's not in my area of expertise. I don't know if Jason could add anything to that, but
there's another aspect of nuclear fuel. It's kind of like the waste that produces. Then there's also the water waste as well. So Matt touched on we're on a free plant, but we're also looking into is potassium hydroxide rather than lithium hydroxide. One of the benefits of that is then we can remove or reduce the tritium which is produced, and tritium being a radioactive isotope of hydrogen has limitations to how much you can dispose of. You can't dispose of that in ion exchanges. It normally goes into things like seawater, freshwater discharge. So changing to potassium hydroxide removes that tritium. So that helps us from our waste management side of things as well. And we can reuse and recycle our water within our own plants as well. So then we don't need to produce as much as that clean water. So there's benefits
question.
Containment, primary and secondary containment on small dispersed land-based installations.
Yeah, so
you can learn a lot from make experience.
Yeah, so obviously containment is a concern. We've got in terms of modularizing containment, that's something that we're all doing. And how that containment structure kind of goes together. It's obviously you've got in a naval application, you've got one of which is the whole something, one of the reactor compartment, and then like you say, it's in the water. That's again, you're a bit out of my comfort zone in terms of expertise, I would say, but I don't really have an answer for that. I don't think. Jace, do you got anything on that?
We've got the containment vessel around here.
Yeah.
Structures surrounding the containment vessel, and it got the arms of the actual structure of the power station. So we touched on that protects us against aircraft impact. So there is levels of containment. I say the same number of levels you'd see in a submarine, but yeah, they're just different types of. So we can use civil structures a lot more in this design than we could use.
Yeah, a little bit. The design of the kind of shape and the design of that sort of has the shield there and the internal containment that's within it. That's all very deliberate. It looks pretty, but that's all about deflection angles. The sort of build up of the burn here. That's all around protecting against things like tsunami sort of issues, but also some land-based threats in terms of someone driving a big lorry and lots of explosives and that kind of thing. So there's lots of functionality built into that architecture, into that terrain. You take that. I wasn't aware of before I came into the project. I thought it just makes it look nice as an investment, but it's very detailed around that architecture.
We always build one just off the coast in Scotland, partly underwater. It was present for Scotland. Take it that way.
Can I ask a very naive question? These are described as small modular reactors. I thought, well, nuclear submarines, particular size, and then we see this as two football pitches. Is the reactor in this nuclear vessel same size as what you've got in the submarine?
No, it's not. No, it's not. It's bigger. It's probably I can really say about that. Yeah, it's bigger, and I mean, really the drive around the size of this, like I said, is very deliberate around setting the maximum power. So the maximum power is obviously trade-off against how you get that cost of electricity down. So it's all of the obviously costs that go into that, but also then how much power you can draw off. These, like I said, they're delivering about 400 sort of megawatt thermal, enough to power a city the size of that Leeds, about 1 million homes. It's what that kind of can power. So that's very deliberate. So now it is a bigger reactor than a submarine reactor.
We've got Mark. We've got a question.
A couple of questions for our online audience, about 30 people on this evening. Firstly, talk about power density of the installation. Presumably, that is controlled by fuel choice as well. Are you limited there by non-proliferation concerns? And secondly, another question is who are your main competitors for this design investment?
Proliferation, question. I guess I can answer that. Yes, in short, yeah, you know, we disagree. We're absolutely bound by non-proliferation sort of agreements and things that we need to be bound by. We are choosing a sort of fuel technology that is understood, that is well known. You know, it is low sort of enrichment. We're not in a super enriched kind of design for fuel, and we're, I guess, using that proven technology, we are going to sort of fly with the kind of regulations and the sort of procedures and the controls and things that are already in place. But, you know, we're not developing a new fuel concept. The way we ended with those ground up sort of views of how we control that. So yes, in short, but that's kind of why that technology has been selected. In terms of competitors, I mean, we wish we can remember it. NewScale is probably one of our biggest. There's stuff, you know, talk coming out of China that there's potential options there, but yeah, I guess NewScale is probably the biggest one.
It's a very different design.
It is. It's a different animal.
It's very, I'd say, even more compact design, but certainly in terms of that inspection, it brings difficulties. Yeah. So maintenance scheduling is more challenging.
Yeah, like I say, though, I guess, you know, the demand for this technology, we've got some projections, obviously, and projections, so I'm not getting too excited, but, you know, we're talking potentially 4 power stations a year kind of numbers. I mean, that's unprecedented in this industry, you know, in terms of delivering some of the items that we need to deliver. For a year is, you know, quite a staggering sort of challenge in terms of supply chain capacity and things like that, and manufacturability. So, yeah, there's room, I think, for competitors in this space. This is you know, we saw the numbers, the figures around electricity demand. They're only going up as we develop further and further. So there's room for renewables, SMR, and there's room for some emerging technologies as well.
Okay.
So we're designing for 60 years. We've got some challenges in there. Certainly, more on 3 gives us a few challenges in our 60 years. But yeah, that's essentially where we're headed.
You?
The conventional PWR large-scale power stations keep hearing stories of corrosion problems with the more stainless type of materials, and also problems with simple carbon manganese steel, things like in. Will your switch from a military to a civil create more problems, or have you already solved them?
I knew I brought it.
So one of the key themes that we're doing from like a material selection point of view is trying to standardise the proven materials to where we and obviously learn from the past. So yes, obviously stainless steel, lots of stress corrosion, cracking has existed in the past. So we're making sure our selection is using like the low carbon variants. We're improving our design so we don't put stress in particular key welded regions, or so we don't have particular pipe lengths. So we are learning from the past. There's still some unknowns on some of the material selections, I would say. So things like the alloy 690, we know it's much better than the alloy 600. Nobody's taken it to 60 years life yet. So we are putting in provisions in place of what is known as like best practice, so tightening up. So we're designing it to the ASME code, but we are putting in additional restrictions for at the start of life, so controlling our chemistry, our manufacturing to make sure we get good uniform mag structures, nice and homogeneous chemistry, and just reducing trace elements where we can to give us the best, obviously, well, the best of what's out there in terms of good practice, but getting that 60-year life. So yeah, a lot of it is learning from the past, and the O&R, I guess this is where they're quite good, is they're very key on, have you learned from things like the Dave Bessie incident? Have you learned from your alloy 600? Have you developed your alloy 52 welds for your alloy 690? So we are taking that forward, but keeping the material list down to a minimum, so then that can reduce your variance, reduce your number of types of welds, it can reduce your number of weld qualifications, your inspection types. So to really bring it down to a manageable number for the critical items.
Now is the whole standardization philosophy. Jay's touched on a few of the sources, but we are, embedded in a lot of the data that we can get from in terms of tier test data and all that sort of stuff. Environment programs going, we'll develop and build more tier test programs as well. It's very much in that proven technology sort of realm where we're focusing our efforts.
So one final question from me, Matthew. You'll be glad to know it's not technical. The sort of profile you put for the growth once the investment hits, where you're going to go from 100 to 1,000, I think you said, so tenfold across 2 years. Is that something that particularly frightens you?
Yes, absolutely. Yeah. You say when that's going to hit, that's it.
Yeah.
We announced from 2 weeks ago.
Yeah.
So yeah, we've got the plans, we've got the profiles, we've got the resource demands, we know exactly what they are. And yeah, they're terrifying.
Yeah.
Especially when, we've got just over the river, in Derby, we've got a submarine sort of enterprise that's growing as well. So
Yeah.
in terms of the skills, we see that's demanding nuclear resource. They're not. That's the key challenge. That's the key challenge. We're going to be robbing Peter to pay Paul a little bit in terms of resource and expertise. Yeah. Anybody want a job? Like, I'm quite happy to talk to you about that. Yeah, we've got a big challenge, and it's not just in my area. That's across the whole power station. There's a lot of digital infrastructure targets, a lot of manufacturing capability needed. Yeah, this is a serious undertaking, no doubt in that regard.
Yeah. Okay. Well, excellent. Thank you.